session will be recorded for your information for future reference. Right. The target for this week, actually, if you look at the content shared e-learning, we have three-phase power measurement technique per unit and also power flow to be covered week 4. Looking at the section, we have I shared to you some of the important videos that you can have a look, especially on each of the content that we intended to cover for week 4. First one will be the watt meter methods, 1 watt meter, 2 watt meter methods for the power measurement, three-phase power measurement, and also some of the calculation involved in the measurement techniques or for the 2 watt meter measurement. And this is very important for, one of the topic that we should cover is the per unit system, because if you miss this per unit information, you having a difficulties later on in order to analyze the power flow, because we have over here power flow topic also will be covered here in week 4. But we not going to cover this week. Maybe somewhere next week we will have we will continue what we missed or the thing that we could not cover due to the holidays for Hari Raya. We have bus admittance matrices. Also, if you look over here, it's only part 1. Actually, if you want to know more about the topic, especially on the matrices, admittance matrices, you can follow the YouTube channel. Over here we have, I got it from General Pack YouTube channel. So it's very good YouTube channel that you can watch to get ideas, or maybe to get clarification if you cannot really understand, or you cannot really digest what being delivered based on my session, as well as based on the lecture notes provided to you. Same goes to the power flow topic also. We have on the part 1 over here, you can have part 2, part 3. If I'm not mistaken, this series, there will be 3 parts for the power flow explanation. All right, getting into the lecture notes that I have over here. I've shared to you the lecture note for this week. And this week, basically, we try to cover 2 portions of it. However, since we cancel, we will postpone our class on Thursday. So our target here today, try to finish this part lah. We try to finish this three-phase power measurement techniques content. And I also leave you guys with homeworks where, as usual, need to be completed manually, in handwritten form. And also you need to have the file name according to the guidelines that I have over here. How do I erase this one? Okay. Any questions so far from you guys? Oh, not to forget, I also provide you with some of the example that we will discuss here today. So hopefully, if you you can get it. You can go through the example later on. just by download the PDF file that I shared over here. All right, back to our target for today. Okay, can you see like this, or you need me to have presentation slide presentation like this, slideshow? Are you there?
So both should be fine.
Is this actually I don't know which screen that I'm sharing, so I need to get your response. What? Which one do you?
This one much better.
This one, sir.
This one is the slideshow view, right?
Slideshow.
Yes.
Yes, sir.
All right. Okay. Okay. Now, shall we begin? Right. The target for today would be the topic that we try to cover is on the power, three-phase power, and also measurement technique. As you can see from the e-learning portal, measurement techniques. Maybe we will discuss on 1 watt meter and also 2 watt meter measurement of three-phase power. Actually, we can also use 3 watt meter as well, but it's very straightforward in that case. So we are focusing on 2 watt meter technique here in this class. All right, for power imbalance three-phase system, as you know, for AC, we will have like 3 definition of power. First one will be active, reactive, and combination of both active and reactive. We can say it. We can reduce it into what we call as complex power. And must remember that active power is basically the real part of a complex. Let's make an analogy like complex number. The real part of the complex number should be the active power, and the imaginary part of the complex number will be the reactive, the magnitude of reactive power. And the active power, also sometimes known as real power, average power. So you must take note on that one as well. If asked about average power, meaning that you are trying to calculate P, or active power, and the units will be in watts. So this is the equation in order for you to get active, reactive, as well as the complex power. For the first one that you see over there, as three-phase, and we have the magnitude sign, meaning that the magnitude of our effect or our complex power or the apparent power can be calculated using 3 times V load times I line. And for the three-phase active power, the inclusion of cos theta at the back, and for the reactive power will be inclusion of sine theta towards in our calculation. Okay, I'm letting someone to our session. All right, let's continue. And if you notice, one of the can I there's a pointer? Yeah. Okay, over here. Okay, over here we have 3 VANIA, and you see here there is sign or symbol over here. Symbol over here means it's a conjugate quantities of IA. And in general, or in overall, we can say that this equation as three-phase is basically a vector equation. I mean, this should be a vector as well as this one should be a vector as well. So, and by looking at what we have over here for Y load or for star connection load, we are using VAN, or basically this is V phase. Okay, and for the current, this is basically the phase current that we are using for calculating complex power. And for delta connection, you see here it's line-to-line voltage measured over here. However, you must remember that line voltage is the same as phase voltage for delta connection. So here we can say that this also is a phase value, V phase, and of course we are using the current that flowing through each phase. So this should be IAB is the phase current. Okay. Okay. Right. Okay. Phase current. Huh. All right. Now, how do I remove these pointers? Next. All right. In general, okay, if you try to use, actually you can use both phase quantities as well as the line quantities. If you're trying to use the line quantities, here is the equation that you can consider. And the equation that you see at the above it is basically using the phase quantities or the phase value of the, whether it is Y or delta connection connected loads. The same goes to other definition of power. We have reactive power. If you consider using the phase quantities, we have 3 times V phase I phase, meaning that actually this is single phase. This is single phase, and we try to multiply it with 3 to get the total 3-phase reactive power information, 3-phase power information. And same goes to active, real, or average. So you will have 3 times V phase I phase cos theta. And please remember that the units for apparent power should be VA. The unit for our reactive power, which should be VARs, and the active power should be in watts. And also, this reactive power can be a positive quantities or a negative quantities. However, for active or real, or sometimes called as average power, we only have a positive value of it. Okay, right. Okay. For the power factor, and if you look at the previous slide, here we have cos theta. Actually, this is information of power factor that we have over here. Here. Try to do it as pen. Okay. Basically, this is the our power factor equation. And again, looking at the data over here, same goes to data that we have over here, basically coming from the subtraction between angle of our voltage and also angle of our current. And this brings to the definition of basically this data is actually the information that we got from our phase impedance. So we can say that this theta is basically theta Z. And yeah, to calculate a power factor, we need this cos theta. And here I put it as theta Z for the power factor, cos theta that we need to use for the power factor. And again, this the theta Z is defined as the difference between angle of voltage and angle of current. You cannot put it the other way around. It should be V minus I, because we from the Ohm's law we know that V equals to IZ, and Z is basically equals to V over, wait, what happened over here? Right, try this. Okay. Okay, Z should be equals to V over I, and considering these two are vectors, so we're gonna have theta V over here, and this should be theta I, and this Z also coming in its complex form, where Z also coming with its angle as well. This should be theta Z. So this is why we say that, oh, it cannot be I minus theta I minus theta V, because if you do that, meaning that you have the opposite or the negative value of the theta. Although in terms of finding the cos theta, it's okay, because cos theta negative still got a positive value. However, you might find it, um, you might got it wrong, considering you try to calculate the reactive power. So please stick to what we have in terms of arrangement, which theta should be minus the other theta. Okay. And other than that, the power factor can also be calculated using this equation, P divided by S. Remember that this S should be the apparent power or the magnitude of our complex power, and P always as a positive value. And actually, I should put it this way as well, the magnitude of our active power. All right. Any questions so far? A question? Okay. Looking at the first example here, we have example 11, where consider this one should be a balanced load, Y-connected balanced load with given values of its impedance as well as the line voltage. We have Kavinish, are you requesting for annotation? Should I approve or decline? Guys, are you there?
No, doctor, it was accident.
Okay, okay. No problem. All right. Looking at this example, actually, I want to get into the solution straight away. However, before we get into the solution, we look at the question first. We have our impedance over here, which is given as R equals to 3 ohms and XL equals to 4 ohms. Just a quick question to you. in terms of power, in terms of reactive power that we try to calculate later on, is it a positive value or a negative value of reactive power? Can anyone guess? Anyone?
Positive.
Yeah. Thank you so much for your response. Who's that?
Leong.
Again? Can you type your name in the chat box so that I can record your participation for this class? Okay. Thank you, Ka Leong. All right. Now, given that this is the circuit, we have Y connected balance load. Our line voltage is 173.2 in magnitudes, and of course, in angles, it will be difference between lines. And the question asking about the average power of each phase and the total load. Average power means that we need to find P and also P total of the connected loads. And the second one, we need to calculate the reactive power, again, each phase as well as the total reactive power. And later, next will be the apparent power, and finally the power factor of the load. Since you answered me that the reactive power should be a positive reactive power, in terms of power factor nature, what would you expect for the power factor? Is it lagging power factor or leading power factor? Anyone?
Lagging.
Lagging. That
Lagging. From.
who's that? Mahesh. Is it Mahesh?
There's another person before me.
Oh, okay. Who's the person? Okay. Thank you. All right. We get into the solution. Can you see one that I'm presenting? Okay. All right. According to the question, right? This is the question. I think it's better for me to put it as PDF, right? Okay, so that we can can you see the PDF version of it?
Yes, sir.
All right. This is better. I think it's easier for me to change the screen. All right. For example 11, I would really recommend you guys to start with list down the all the information that you have from the question. And if you look at this example, yeah, the first thing that I will do is I'll try to identify what kind of connection do I have. Here we have star or Y connected. So I have to get in my mind that, okay, the line voltage will be slightly different with the magnitude of the phase voltage. So with the information of line voltage here, I list it down first, like here. Okay. And the next thing I would do from this line voltage, I straight away getting my phase voltage, all my phase voltages. So why do you think I put the phase voltage? Because if you remember in our last class, I reminded you that our calculation should start from phase, no matter is delta or star connected loads. So you need to have the phase voltages information in order for you to use the Ohm's law to calculate current, maybe to calculate the impedance. In this case, maybe impedance were given. Then we need to use the phase information in order to calculate our current. So this is the first thing that I will do. This is my second thing that I'll try to put in my solution. And the third one will be the current. Okay, the current calculation where I will use my phase voltage information as well as the impedance information for each phase. So here, since our connection was a Y connected load, so we can say that if I have the phase current, then it will be the same as the line current. So that's why here I put it as IA, where IA is normally we can call it as the line current, but yeah, it's the same as the phase current since the connection is Y connected. And another question, why I need to find the current? Okay, it brings me to the solution of the first question, asking about the average power. You know that the average power is basically P that we try to calculate. So to calculate P, we need the information of voltage, current, and also the cos theta, and actually the theta information lah in this case. So here, the voltage and current, actually this equation, in general, this equation actually referring to the phase information. Okay, so that's why you have here P1 phase. Okay, single phase active power or single phase average power. All I need in terms of the values, all I need in terms of the value is just the value of phase voltage magnitude, phase current magnitude, and also the difference between theta V and also theta I here. Okay, so theta V is negative 30 and theta I is negative 83.13, looking back at our solution 4. And if you notice, if you convert this Z into into a polar form, the theta Z that you can get from here is basically theta Z that you seen here is basically the value that you see over here, 53.13. My point is that, hey, this 53.13 is basically our theta Z. So maybe later on might need it, or if not, yeah, it's for your information lah. But it's very good that you really understand that this data is basically coming from the angle of our impedance. You can see the importance later on in other example lah. I will show you. Okay, okay. To cut short the details, here's the calculation, and for the total three-phase power, basically we just include 3 times of our phase average or phase active power to get the total three-phase power in this case. And I think it's easier, it's more convenient compared to if you try to use this formula in order to calculate, using the line information in order to calculate your three-phase power. Maybe you later on you can try by your own lah, and compare whether this formula is the same, will give the same value compared to one that we've seen using the line information. It's for you lah to check it back. All right, same goes to reactive power. We are still using the phase information for the first single phase reactive power, or reactive power for each phase, except that here we use sine theta, okay, and since our data over here, we understood that coming from theta z or theta z, the difference between theta v and theta I, very straightforward lah. Put all the values over here, and bam, you get 960 VARs for single phase reactive power. And to get the three-phase or total reactive power for the load, the three-phase load, just times with 3, and we will have this value. And as predicted by our friend just now, yeah, we'll have a positive value of reactive power. Okay. And for the apparent power, you must understand that apparent power is the magnitude, okay, the magnitude of our complex power. If you don't put the magnitude symbol, I still will accept that, but you need, in terms of your understanding, you need to understand that this is a magnitude. We don't have any angle over here. Normally, S, if you consider S as a vector, normally it will come with the magnitude, okay, and also the angle of the complex power. Later on, you might find that, hey, this angle is actually the same value. Later on, you might find it, you can conclude that way. But at this point, just, understand that there is a difference between apparent power and also complex power. Apparent power is, we are referring to this portion of the complex power, the magnitude portion. Okay, in terms of its calculation, is very simple. Get the magnitude of voltage and current for the phase. Again, we will start the calculation from the phase quantities. So here, the apparent power for single phase is 2000 VA, and for the three phase, we have 6,000 when we multiply the single phase with 3. And for the power factor, last example, last in our example, we need to calculate the power factor. You will see that actually there is the value of power factor, whether it is in if you consider it single phase or three phase, the value should be the same value. And there is a reason why I asked you about this, whether it's lag or leading, because power factor should come with two information. The first one will be the its magnitude, and the magnitude should be in between 0 to 1. And another one is which is very important to um, to show us what kind of load that we have in our system is the nature of the power factor, whether it is lagging or leading. And lagging is due to the nature of our impedance, which coming from RL components. So here we have power factor calculated using a single phase strategy, and another one calculating using three phase information. And the best way to calculate this is by using P divided by S. And if you consider a single phase, you must use P single phase divided by S single phase. And if you try to calculate using a three phase strategy, you must use P three phase divided by S three phase. And yeah, if you look at the definition that we have for the power factor also can be calculated using this formula, cos theta Z. And if you notice here, you can also use theta Z, cos theta Z to get your power factor. All right. Any questions so far?
Okay, doctor.
Okay. Easy, right?
Sir.
Yeah.
So why is the power factor lagging?
The power factor, I think I did mention it. The power factor is lagging because of our impedance over here, where we have RL. And if you refer back to CIVIL, okay, we are focusing on this portion that V will always lead the current. And for the power factor, we are considering voltage as our reference. So here we can say that for this kind of arrangement, okay, I'll try to write it here. Here, I will always lag. Okay, I will always lag the voltage. Okay, so using this definition, we will use the same definition for the nature of the power factor for the system, or for our load over here. Is that do I need to clear things up again? Is it okay with you?
Yeah, thank you, doctor.
All right. Right, we have another example. Okay, over here, looking at the example, here we have three-phase motor, balance load. Yeah, that's information. And the three-phase motor draws 5.6 kilowatt when the line voltage is 220 volts and the line current is 18.2 ampere. Now, you need to determine the power factor of the motor. All right. My question, before I ask you, maybe this is the first time you guys saw this, see this. Okay. If it is mentioned like this, a three-phase motor draws 5.6 kilowatt. There's no information of the three-phase motor draws 5.6 kilowatt per phase. Doesn't mention per phase. Yeah. So we can say that this information is the three-phase power information. And since it is kilowatt over here, okay, it is the active or the average power. Active, average, another one is real power. So you must read the information or information given in the question. You should understand it very well. Otherwise, you will doing the wrong direction lah. Okay, that's one. And yeah, the rest will be very obvious. Okay, that's one more thing. It says that the three-phase motor is a balanced Y load over here, or balanced star connected load. And here we have V line. Okay, here we have V line, and here we have line current, which is I line. And actually, there is other information that you also need to understand, or you need also to aware that this I line also can be regarded as our phase current as well. Okay, that's another thing. And one more thing that you also need to have in mind, that since it is a balance, the keyword here is balance. It is balance, meaning that if this is three-phase power, which is 5.6, I put it as 5.6 over here. If I try to find P single phase, just by divide by my three-phase power by 3, yeah, I will get my single phase active power, or the power information for each phase. Okay, right, enough with the explanation about the question. We get into the solution. This is what you should imagine lah. So we have a three-phase Y connected motor. Y connected loop, which is the motor itself. So as I mentioned just now, the information that we have the three-phase power, which is 5.6 kilowatt, and we can straight away get our other information that not being given in the question, which is the single phase power, which is 1,866.7 watt when you divide it by 3. Other information that you need to aware, which is the line, and also from here you can use this equation where V line equals to, I have to write it, that from third 3 times V phase. Okay, this is in terms of its magnitude. Okay, the magnitude of V line is also equals third 3 times VP. So that's why I have it here, the V phase as 127.0. And what is the question actually? Determine the power factor of the motor. So if you look at my strategy over here, in order for me to find the power factor, okay, I know that my power factor is coming from this equation, which is P divided by S, and it's up to you to use the first single phase phase information or the three-phase information. Here I use the one phase information or single phase information, where I will use this P single phase divided by S single phase to get my power factor value here. Maybe you will also would like to ask about how do I get or how do I know that my power factor is lag? Okay. If consider this is a motor, so if you consider it is a motor, meaning that it always going to be a lagging power factor because motor, the build up of the motor should comes from coil inductors. So we can say that the motor itself, in terms of the nature, it can be represented by RL load. Okay, except for one topology of electric motor, which is known as synchronous motor, where synchronous motor, the power factor being supplied by or go back and forth. If we have the synchronous motor, would be a negative value of reactive power. So our power factor later on will become lead power factor. That's another case. But in most cases, in most industrial applications, motor have been applied in industry. Most of it comes from the topology known as induction motor, where induction motor always can be replaced or can be modeled as an RL load. So at the end, power factor, a lagging power factor. So if you look at the solution over here, the first part written in blue, actually using the phase information. And if you look the one that I have at the bottom over here, I'll try to use a three-phase information, okay, to calculate the power factor. And to calculate the power factor, yeah, we need this equation where we need information of our active power as well as the apparent power. And the active power given in the question as 5.6 kilowatt. However, for the apparent power, there are two ways to calculate. The first one using the phase information, 3 times V phase I phase, or you can also use the line information. Here we have set 3 times V line I line. So you can use either way lah, provided that you must use this equation in order to get your power factor values. Okay, any question? Before we get into next one, any question? I'll proceed, yeah. All right, for example 13 will be your homework for this week, as well as example 14. So you should able to complete your homework lah, since we discuss on the powers for three-phase system. Okay, we get into our second part of session will be the measurement, power measurement, three-phase power measurement. As I mentioned early in the session, three-phase power system can use a single watt meter, you can use 2-watt meter, and of course, it is obvious that since we have three phases, yeah, we need 3-watt meters in order to get our power for the three-phase power information. And for the 1-watt meter, maybe you should consider that the system is a balanced system. Other phases will be identical. Phases will be identical with each other. So enough with on using 1-watt meter, and the rest we just multiply by 3. Okay. Um, we are focusing on 2 watt meters lah, because 1 and also 3 is very straight forward or very obvious. So we are trying to discuss about 2 watt meters. Basically, in order to in industry lah, normal practice, the load will be unbalanced. Yeah, although our generator will be a balanced supply, but on the load side, it's quite difficult lah, in order to get a balanced load for the 3 phases that we have. So yeah, the obvious solution for that, we should have 3 watt meters in order to measure the total information, the information of total power for our 3-phase system. However, that one is not very cost effective. So there is a way we can consider more cost effective compared to using 3 watt meters, which we try to reduce the uses of a single watt meter out of from the 3 watt meters that we think that one should be the ideal solution for our problem. So for the 2 watt meters, we try to set up 2 watt meters, these 2 watt meters in order to measure the 3-phase system. And the total real power or P total can be found by taking the reading of first meter and also the second meter, we sum it together. So P total coming from P1 plus P2. The name itself, it's a watt meter, meaning that it will give you the information of watts or the information of active, of average or real power. In short, you can only get P from the watt meter. Okay, how it is connected? So this is how it is connected. We have 2 watt meters connected at one line, 1 watt meter. Let's say we consider P1 connected to one line. Let's say line A, and P2 we connect it to line B, and the third line over here, or line C, it's a common point where we try to take, actually this one, okay, will be used to measure the current, okay, and this one will be used to measure the voltage. So one end of the voltage will coming from the first line, and the other end will coming from the common line. So we can say that, yeah, I think it's very, you also understand that to measure the voltage, we must put a voltmeter in parallel, right? So this is the connection or the arrangement of voltmeter that we have for watt meters. And the ammeter, to measure the current, we will put the ammeter in series with the circuit. So this is why I say that this is representing the current or measurement of current, and this is representing the measurement of voltage. And in practical, actually you don't care about the how do I connect the ammeter and also voltmeter, because the wattmeter actually comes with only with 2 terminals. So you just connect it, one over here and another one over here. It's very easy. Actually, it's 3 terminal. It's very easy lah, to set up the wattmeter in order to measure the power, 3-phase power. That's one kind of connection, and this also one kind connection that we can consider. If you notice, we also have a common line over here where Here we try to measure the voltage, and also over here we try to measure the voltage as well. All right, and in terms of what we will get, okay, what we will get from the wattmeter, actually we will get the P or the active power for P1 actually reading over here, and P2 that we see here is the reading for the second wattmeter. Right. I don't want to get into details of the one that have in the text over here. What I'll try to highlight is that the power vector, you must remember that is coming from theta Z, and from the calculation and so on. If you read through this, you can see that in the end, the value that you see over here, which is the P1 value, can also be calculated using this formula. Okay, P1 is VL cos theta Z plus 30. And why plus 30? The reason is over here. Here it says that we recall that each line voltage lead corresponding phase by 30 degrees. It's because of the phase and line difference, so of the connection. And thus the total phase difference between phase current IA and the line current VAB is theta Z plus 30 degrees. Okay, so actually this is what being mentioned in this tag. If for you as a student, I think better you understand that P1, okay, can be calculated using this equation. On the other hand, for P2, for wattmeter 2, and sometimes it's P2, sometimes it's W2. Same also over here, sometimes it's P, sometimes it's W1, okay, watt 1. Here it's mentioned. All right. You can calculate the value of display over here by using this equation, VLIL cos theta Z minus 30 degrees. It's slightly different with what you have in P1, where in P1 we have theta plus theta Z plus 30. Here we have theta Z minus 30 degrees. So please remember that one. And in order to calculate the total power, as I mentioned before, we just take the summation of both P1 and P2 to get our total three-phase power, and also can be calculated using this equation. Okay, so 3 VLIL cos theta Z. Again, theta Z is here. Okay, it's very important, the impedance information. All right, now we can say that in order to have our total three-phase power, active power or total average power, reading that, let's say I have reading over here, let's say this is 10 watt, and maybe this is 20 watt, maybe, no. Okay, total active power or total average power or total real power, I would say it's 30 watts, because 10 plus 20 will lead us to the total average power in this case. On the other hand, for I don't expect you guys to go through the derivation over here. It will involve trigonometry, identity. Yeah, I'm not going to get into that. Maybe if you want to know details, you can go into that one. In fact, in the videos that I shared also discuss about how from P1 plus P2 get into this equation. I mean, how from, okay, how from here we get into this. Okay, so you can have a look. But what I can say here now is that as long as you know that total power is coming from this equation P1 plus P2, and this P1 plus P2 also actually coming can be defined as this equation, which is 3 VLIL cos theta z, then that should be enough for this course. And for the second wattmeter, sorry, not this wattmeter, for the information, other information that you can get from the value of, let's say here we have 20 watt using the 2 watt meters lah, based on this setup. What are the information that we can get? The first one, yeah, of course, the average power P, and another one we will also can calculate this reactive power, three-phase reactive power, where three-phase reactive power, maybe you can go through later on the derivation of this. The three-phase reactive power is given by this equation, 3 times P2 minus P1. If we consider the values as I make for example just now, to get my Q total, I will have like 3, 20 minus 10. So 3 times 10 lah in this case. And also, if you look before this, when we learn about three-phase reactive power, the Q total is also can be written as this equation. Yeah, you must also know that Q total is defined as 3 times P2 minus P1, and is equals to 3 V line I line sine theta Z. Again, theta Z is very important. Okay. Yeah, since we have the power, active power or average power over here, and also we can, later to that, we can calculate our reactive power. By using the Pythagoras theorem, we can calculate the apparent power. And I must say that this should be the magnitude of our complex power. And since we have all the information of P, Q, S, we can also get the power factor, where power factor is given by cos theta. Please remember, power factor is cos theta. And the one that you see over here is the way to calculate the theta itself. Theta z coming from tangent Q total divided by P total. Okay, how do it come across? Yeah? Okay, remember the power triangle that we have over here? The one that we have for the horizontal line will be the active power. For the vertical line, we should have the reactive power, and the diagonal line will be, the diagonal vector will be our apparent power. And here is the theta. Okay, theta. Oh, like I'm drawing using my data. Okay, this is theta, and this theta is basically theta S. What I'm trying to highlight here is that theta S is equals to values of theta Z. Okay, this is something outside most of the textbook. So if you think about the angle itself, actually theta S is the same as theta Z. All right, in other words, how it become tangent theta, because we try to find the theta over here. So the opposite of it is the reactive power, the Q, and the adjacent will be our active power or our P, right? And expanding from that one, we know that Q total is 3 P2 minus P1, and the P total is P2 plus P1. So based on the 2 watts or 2 watt meter that we have earlier, we might think that, okay, we only have the information of P. But basically, from the information of P, we can get all information of the three-phase power for our load. We can get reactive power, we can get the apparent, as well as the power factor. And how do you know the power factor is a leading power factor or a lagging power factor? Again, it returns back to our Q over here. If Q is positive, okay, if the one that you calculate here is a positive Q, okay, you can say that our power factor will be lagged. Okay, and if our calculation over here, where we have maybe P1 greater than P2, and this equation will become negative value. So if this is negative, we can say that, okay, our power factor will be a leading power factor. Okay, leading power factor over here. So yeah, other than that, maybe you can also use this. If P1, P2 is equal, you can say that it is a resistive load. P2 greater than P1 is inductive. If you want to remember all this, then it's up to you. But the way I remember it is just by looking at my reactive power. If my reactive power is positive, I know my impedance will be RL, coming from RL. And if my reactive power is negative, it's coming from RC, or impedance is most likely RC. Okay, one of the disadvantage of this 2 watt meter here, it says that cannot be used to measure a 3-phase 4-wire system. Okay, cannot be measured unless kita buat dia kan, mesti boleh punya lah. Unless the current through the neutral is 0, meaning that it's a balanced system lah. If it is a balanced system, then 2 watt meter, it's a good way, economical way to call it, to practice lah, the best practice lah. All right, yeah, otherwise we need to use 3 watt meter, blah, 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 blah. Okay, 3 watt meter also being discussed over here, but we're not gonna get into details on that one. Yeah, we also, this is more advanced, where we have PQS measurement, specifically measure each of the quantities. Of course, this is better. Yeah, this is better compared to 2 watt meters, but it will cost you more lah. All right, example 15, considered as your homework. Yeah, we will discuss example 16 over here. Looking at the question, we have line voltages, VL equals to 208 volts, and the wattmeter P1 equals to 560 watt, P2 equals to 800 watt. Assume load is Y connected. This is part of the question. This assumption is part of the question. Determine the total average power. I think it's very straightforward. For average power total, just get the summation of P1 and P2. And for the total average reactive power, we include the SMJE1103 and P2 times it with P2 minus P1. And for the power factor, we will use that tangent kind of thing to get our power factor. And for the phase impedance, yeah, you can maybe use the voltage, line voltage, as well as the other power information over here in order to get the phase impedance. And yet, and later on, deduce whether the impedance is inductive or capacitive. So let's see the example. I mean, the solution. This is what told to us in the question. We have to use 2-watt meter. I mean, the setup is 2-watt meter, where information of line voltage we have there. We have the information of P1 and also P2. So here, as we discussed just now, for average power P total, we just get the summation of P1 and P2, and bam, we got it, the value. And for the reactive power, we must use this equation where we have SMJE1103 and also the difference between P2 and P1. You cannot do it the other way around. You cannot do it like P1 minus P2. You cannot do it this way. You must use P2 minus P1. Okay, this is based on what had been proved or what had been derived earlier based on this derivation. So if you use P1 minus P2, you will end up with negative VLIL2 sine 30 degrees sine theta Z. So it's still not finished until you bring the negative sign over here, and by using the trigonometry identity, you know that this portion, okay, this portion is basically the sine theta Z. Okay. All right. Anyway, we're not going to discuss on the derivation. Later on, you can find it by yourself. We try to solve the direct question that we have over here. Okay. Remember, you cannot do this. Yeah, you cannot do P1 minus P2. It's always P2 minus P1. Okay. And for the power factor, we will use the tangent, arctangent of Q total divided by P total. And we have the information of Q total and also the P total. With that, we will get our theta, where theta is considered as theta Z. And with this theta, okay, we will plug into the power factor equation. Cos theta is 0.96. And again, how do I know this is lagging? This is because one, maybe this is a positive value. Okay. If you do it the other way around, you might get different answer lah. You might get a negative value of your Q total. You will incorrect at this part, and also you might be wrong here as well. So please be careful later on when you try to set up the equation of the reactive power. And another way to look at it is by the definition that I have in the slide earlier, where when P2 is larger than P1, yeah, when P2 is larger than P1, of course, this part will be a positive value. And since this is a positive, yeah, Q will be positive. And Q positive, we will have a lagging power factor. All right, that's for the power factor. And for the phase impedance, you know that earlier we calculated our theta Z. And for phase impedance, yeah, normally we will have like this, yeah, Z equals to R plus JX, right? This, of course, will be plus. It's not going to be minus because this is positive vars. So it always going to be plus over here. If this is minus, it will be negative JX. So this is the rectangular form of our impedance. We can also write it in a polar form, okay, where in a polar form, here we have magnitude of Z, and here we have a theta Z, okay, right? Theta Z, yeah, based on what we have earlier, we got this one. Our target is to get this magnitude of zeta. So if Z, if you look at the solution that I have over here, actually I try to work out the value of Z, magnitude of Z. Okay, how do I start? I start with this equation. Okay, P total set 3 times VL times IL, cos theta is here, which is 0.96 if I'm not mistaken. And by rearranging this one, I will have my IL. Okay, I got my IL. And why I want my IL? Because I want to use this current so that I can calculate my Z. However, I must have in mind that since this is a delta, sorry, not a delta, a Y connected load, the IL, the line current that I have over here, is the same value as my phase current. So actually, if you look in the next calculation, where I use this as I phase, basically I phase that I have over here comes from line current that I calculated earlier. Since because of the connection itself is the star connected load, so I line equals to I phase. Yeah, it's the same value. All right, before getting into the value of our impedance, okay, you cannot calculate your impedance based on the line quantities. For example, you say maybe you might try to use this Z equal to V line divided by I line. Okay, this is wrong. You cannot do it unless let's say this is a star connection, star connected load, unless this you change it into a phase quantity where you have like, yeah, of course this I line is a phase quantities, and this one should be V line divided by square root of 3. Use V line divided by square root of t divide by IL, then yeah, it makes sense because this is a phase quantity and also this is a phase quantity, provided that this one is the star connected load. And if this is a delta connection, okay, if consider this is a delta connected load, you cannot also use straight away this formula. Why? Because in delta, yes, the line voltage is the phase voltage. Yeah, we can say that V line equals to V phase for delta. Okay, the voltage across here, okay, is equals to the voltage across this element over here. But I line that we have over here is not the current that flowing through this phase. So we cannot get our Z for each phase by using this equation. What you need to do, you need to divide this line current with square root of 3. Then you can use it. So anyway, it might get you confused later on. So my advice, I would say that I would try to start with phase. Anything that I'll do in terms of finding my impedance, yeah, of course, the impedance will be connected at each phase. I will try to use the phase information. So this why here you see that I have my phase voltage being defined earlier before I get into my calculation of Z. So V phase divided by I phase definitely will related to the phase impedance that I try to calculate. So since I need to just only the magnitude, so I take the magnitude of voltage and also the magnitude of the current, then it will give me the magnitude of my impedance. Now, when you try to give your answer, you must provide both magnitude and also the angle. Again, the angle we didn't calculate over here. We had already calculated earlier when we tried to calculate our power factor. So it is very important that you should understand that cos theta is basically cos theta z, and theta z is also theta of s. Later on, it might, useful for you to know the angle of your impedance. Okay. Any questions so far? Any question?
No, sir.
Okay. It's very step by step, right? I hope so lah. Okay. All right. We have example 17 for your homework and 18 that we'll discuss here today. And finally, example 19 for your homework lah. All right. Let's go to example 18. In this example, we'll go through the question first. The load is delta connected. Okay, the load is delta connected with impedance per phase, or impedance per phase, meaning that this is, let's say, this is delta connected load. I try to draw it using only a mouse over here. That's why it's quite ugly. So, yeah, the Z that we have over here is basically the impedance for each phase. Now, and we also have the line voltage, which is 440. Let's say this is my A. Let's say this is my C. And this is my B. Or maybe you can put it ABC as well. So can. Maybe we put it as ABC lah. Here, easy for us to know the sequence. Okay, one more thing. There is no information on the sequence, right? So you can assume this one is a positive sequence in terms of the power supply being supplied to the load. You can consider it as positive. Over here. And what we have the Z information, and also we have the line voltage over here, which is B line. And we have to predict the wattmeter W1 and W2. And also towards the end, calculate the total active and also total reactive power. Okay, what is our strategy over here? We need to know this equation, and also we need to know this equation. How do we get that? Okay, remember, in my slide over here, okay, I did mention that these two equations is very important. Okay, these two equations Okay, I draw it using maybe slightly different color. This equation is very important for you to calculate your P1 or W1. And this equation is very important for you to calculate W2. Yeah? The difference will be the one at the top. For P1, we have plus. For W2, we have minus. Okay. Based on what we have in the question, okay, what we have in the question, we only have the line voltage information. We don't have the line current information. So you need to find this first. Find this first, and then you can calculate both W1 and W2 easily. Okay. So that's our strategy lah. So now we get into our solution. This is what we intended in the beginning. What we try to get is we try to calculate using this equation. Okay. However, we lack of this information. So if you look my first step over here, I try to find IL. And if you look at the equation that we have, we don't need the angle of the current. We only need the magnitude of the current. Okay. For those who, I mean, if you are the first timer in terms of looking at this equation, maybe you might think that VLIL should becomes, comes with its angle. But actually, in order to make this equation works, VLIL is just the magnitude. It's just the magnitude. Okay. Now, VL magnitude is given in the question. Our target is IL. IL, since this is the call it delta connected load. So whatever we do related to the phase impedance will give us the phase information. And of course, since this is a delta, we can say that the V line that we have in the question information is also the phase voltage. And when we try to use the phase impedance over here in order to get the current that we calculated is actually the phase current, the current that flowing through this part, okay, this line, this flowing to this phase from A to B, for example. This is the current that you might find it over here. Okay. And yeah, according to the question, we need the line current. The line current is here. I line is over here. And you must know that for delta connection, topology, for delta topology, the relationship between the line and the phase only happen at the current, where the line current would be equals to 3 times the phase current. So this is what happened over here. Okay, why we need this? Because in this equation, it requires us to plug in or to fit in the line current information. All right. Once we got the line current, the rest will be straightforward lah. Very obvious, because we know that theta z can always we can always get it from the information of our impedance over here, where this is our theta z, okay, negative 53.13. And for P1 and P2 can be calculated using the equation that I have over here. Here we have P1 is 6,100 66.6. If you like it in 2 decimal point, fine. If you put it as 1 decimal point, also okay. But please consistent lah. Actually, I also not consistent over here. Let's see. See here. My answer here is 2 decimal point. Here is 1 decimal point. Here is 1 decimal point. Ikut suka je kan. Suppose you should be consistent in your show your answer lah. All right. Now for P1, P2 is very straightforward, and for P total again, since we have the value over here P1 and P2, P total is just the summation of P1 and P2. We will have is 6,966.7 watt as our average three-phase power. Three-phase average power. Okay, three-phase average power. I put it, I arrange it back. And for the total reactive power or three-phase reactive power, we have Z3 times P2 minus P1. Again, please remember it should always be P2 minus P1. Yeah, you cannot do it as P1 minus P2. You might get it wrong. You will get it wrong. You not might. You will get it wrong. Okay, based on what we have over here, can someone tells me the nature? If I try to calculate the power factor, what is the nature of our power factor? Someone?
Is it lagging, doctor?
Huh? Who's that? Oh,
Again.
you. Okay, yeah. The power factor should be leading because our bars over here or our reactive power is a negative value. Okay, leading power factor. But in the question, I just stop at Q total. You don't need to calculate the power factor, but it just come in mind lah. I mean, I just want to test your understanding on this. All right. Yeah. I think that's all for now and for today. Is there any question from you? Any question?
No, doctor.
Easy, right? Very easy.
Sir,
Yes.
may I know, will this video be uploaded in e-learning or like where will you be uploading it?
I'm not gonna
What's it?
upload it.
In the YouTube or?
I'm not gonna upload it.
Okay.
Next semester I will upload it.
Ah,
Hi, why should I upload? I think you, all of you here, right?
is it
Yes, but in case we want to revise, we'll get it back.
Yeah, I know. That's now you're not listening, and later on you will listen back, right? But anyway, don't worry, Riff. I just try to test your patience. I will upload it in e-learning later on this semester.
thank you.
Don't worry. I just want to test your patience today. I think this is the first time we conduct our class online, right?
Yeah.
We had one time online during
Previously, we do
one class.
one.
One class
Only one time, doctor.
Oh,
Semester one, during semester one.
during semester one.
oh, okay. All right. Anyone have scanned the attendance over here? Is there anyone who still missed the attendance?
Yes, sir. I would still want to scan. Just now didn't scan.
Okay, all right. I'll share it to you. Anyway, how do I say it? Actually, this week, Hari Raya, we will we have to postpone our class, and we don't have much time towards to finish until week 7. So I just try to get the idea of, can we do additional class later on after how call it, after, I mean, after 5 maybe? Can we do that? But not this week lah. This week because everyone's Hari Raya, and that's one. Maybe not this week, maybe other weeks. And do you prefer it to be online or physical? Because I think it's quite hard for me to. I don't know. Actually, both also can lah. But one of the method. I'm not going to tell you which method. One of the method, I think I'm not good. Not really prefer lah. It's quite hard. So, is it okay if you have another, additional session outside class hour? After 5 lah. Is it okay?
I'm just with it.
Oh, okay. I just want to get your, get your agreement on this one, because actually after 5 I cannot make any class at that time. But since we reschedule our 2-hour session, maybe we need that 2 hours. But we proceed with what we have. Next week we will continue chapter 4, where we will talk about the second part of it, which is the power flow and load flow. I really appreciate that you have a look at the notes, and as well as try to view the videos that I shared over here. Bukan suka-suka je share ni it's not just put all the videos just make this portal full. It's for you to have to go through it and to study based on materials that I provided. If you're not gonna do that, I cannot do anything. But I know why. In the end, I know the reason towards that one lah. Okay. Anyway, that's all for today. Stop sharing. Any last word from you guys? Anything that you need to highlight?